Very good morning, sir. So this again, my question is, sir, what is the difference between measuring in theoretical maths and applied mathematics?
Once again, could you please repeat that?
Yeah, yes, sir. Sir, what is the difference between measuring in theoretical mathematics and applied mathematics?
What theoretical mathematics?
Yes, theoretical mathematics and applied
I've
mathematics.
never heard that word theoretical mathematics. I've heard of applied mathematics, yes.
Yes, sir. Measuring in theoretical mathematics and applied mathematics. What is the difference between?
Usually the difference is made by saying pure mathematics and applied mathematics. So do you mean that pure versus applied? Hello?
Yes, sir, I cannot able to hear you. Sir, can I comment on my question in comment box?
I can hear you, but
Yes, sir. Yes, sir. I can repeat it. Sir, here my question is: what is the difference between measuring in theoretical mathematics and applied mathematics?
well, actually, as I said, can you hear me?
Yes, sir. Yes, sir. Yes, sir. I am here.
Okay. You see, it is my view that this difference should not be made. But unfortunately, it is made not just in India, world over, to different degrees. Difference, if any, is in concepts which are used, which are introduced to bring forth the basic ideas which develop the mathematics or which develop things which you want to use. Let me give you an example. This question of whether 1 by 0 is infinity or not. Okay? This tells you immediately the problem. 1 by 0 or 2 by 0 or 3 by 0, whatever, cannot be a one unique quantity. That you can immediately prove. But infinity can be made an item, an object, if you want, if you insist on dealing with infinity. So, you see, people often make a mistake between a number and a limit of a sequence of numbers. That is the often mistake. Okay? For example, 1, 2, 3, 4, 5, 6, n. Okay? When you say n going to infinity, what is it you mean? That symbol which is unfortunately introduced, it should not have been introduced, but it is there. That so-called n tending to infinity. What you mean is n becoming larger and larger and larger. It is not that n is approaching some real number. That is the mistake. And that is the fault of the teacher. Okay? So your question is, for example, solving a differential equation. Okay? Is it part of applied mathematics or is it part of pure mathematics? The number of differential equations that you can actually solve by simple functions, which is what you are taught in classes, is you can count in one finger. But number of differential equations you cannot solve are enormous in number. So what do you do? You give up and say that I cannot solve. And that's exactly where power of mathematics comes. In just not solving in terms of sines, cosines, exponentials. How many functions you know explicitly? Extremely small. I mean, how much do you know? Polynomials, exponential, sine, cosine, few trigonometric functions. Is that all that there is in mathematics? Then mathematics is not worth doing. There are many, infinitely more functions than just these few that you learn in class. A good, proper mathematics, applied mathematics too, also, is one which deals with functions which are not just these few functions that you are familiar with from school or college. You have to grow far beyond. That's why I said there is no such thing as pure and applied mathematics. What I should say, good and bad mathematics. That difference I will make, not pure and applied mathematics.
I think there are no more questions. Like there are other questions also, like pure mathematics and applied mathematics, as you have discussed right now. The same similar
I would, for example, add one more sentence to that, which
yes,
is,
sir.
you know, some of you may have heard of Poincaré, as I mentioned. Poincaré is a French mathematician who lived in the beginning of the last century. 1900, I don't know when he died, 19 maybe 40 or something. Have you heard of his name, some of you?
Yes, sir.
Yes, sir. Yes, sir.
What context have you heard? What kind of theorems ascribed to Poincaré have you heard?
Poincaré conjecture, sir.
Poincaré conjecture, because it is very recent. Because there is a medal associated with it and so on. Yes, that is true. Poincaré conjecture is associated with him.
Which was resolved by Russian.
What was the other one?
I think it was resolved by Russian mathematician Gregory Perelman.
Perelman, yes, Perelman. Yeah, that's what I mean. That you must have seen in Wikipedia. But do you know any theorem of Poincaré? For example,
no, I said.
Have you heard of any theorem of Poincaré?
Heard about conjecture only.
What about?
Heard about conjecture only, sir. Yes.
Yeah, Poincaré conjecture is one, but what is the statement of Poincaré conjecture?
No. Don't know.
That is the important thing. You see, Poincaré. Anyway, forget about that. But I was saying Poincaré. Do you know that Poincaré was actually predecessor to Einstein in studying some of the ideas of special theory of relativity? The geometry that is arising out of Einstein's special theory of relativity, Poincaré as well as Minkowski, these two mathematicians, they studied it already before Einstein. So Poincaré also studied electromagnetism. Would you call Poincaré applied mathematician or a pure mathematician? That is my question to you.
He was a mathematician.
He was a top class mathematician. That's what he was.
Yeah.
He was not. He could do both without too much difficulty. But only difficult problems, not the kind of problems that unfortunately many of us do in India. That's why I said, in order to solve the problem which Newton and Laplace did not or could not, he invented the subject of topology. What you study today and call it topology. He invented it. He called it by different name, but that was the beginning of the subject of topology. And to solve difficult problems in applied mathematics, you will need that. You will need a knowledge of topology. It is almost indispensable today. Okay, anything more?
Sir, during the time of Hardy and Ramanujan, number theory was a pure mathematics, but now number theory is applicable nowadays. No?
Very well. Something interfering. Yeah, now go ahead, please repeat.
At the time of Hardy and Ramanujan, number theory was one of the classical subjects, but nowadays it is useful in cryptography, coding theory, all these areas. So now so we can't treat number theory applied as a theory. So it's in his language, as Hardy says, every mathematics is useful and there is no place for bad mathematics.
No, Hardy was saying that for the different reason. You see, Hardy, that was his personal opinion. Hardy was saying this because, don't forget, when was Hardy around? It was just a little before, it is between the two world wars, right?
Yeah.
Late 1920s and beginning of 1930s. So, First World War has ended and Second World War has not started, but things are already getting difficult in Europe. So, Europe was in between two world wars. So, in that background, you have to look at this statement. Because the government, like all governments, they were trying to ask people to do things which they consider useful. Okay, so there was some pressure on mathematicians and mathematics to do things which are sort of considered useful by the government or by the powerful people of the countries involved. So he made that statement, I think, as a counter to that. He said that I do things which are not useful. So he said that as a protest against such things. So you have to understand it in that context. At that time, of course, Hardy did not have any idea that the pure number theory, by the way, Hardy was doing more analytic number theory, okay? What is called analytic number theory, which is what Hardy and Ramanujan both did. Okay? What is more useful now is more analytic number theory is also useful through elliptic curves and things like that. Anyway, by the way, I am not an expert in this area, let me say right away. But what I have learned a little bit is that the more algebraic number theory and just coding part is not really number theory, but you use the elliptic curve theory to do the coding and cryptography. That is true. It is useful. It is used quite a bit in research. And prime numbers are used in coding and cryptography. The present security system, what is called RSA code, is based on prime numbers, which is used everywhere. So that is true. Your statement is true. That number theory, which at one time or even now thought of as a classical subject, it is a classical subject, but it is finding use in many areas. That is a correct statement. Yes, I am.
Still there is a question, or let us thank our
Yes, sir. I have a question.
Yes.
Is there any question for that? Yes,
Please.
Hello.
Yes, go ahead.
Nancy Tiwari.
Yes, sir.
Are
So
you
sorry. Yes, sir. Yes, sir. Hello.
Yes, go ahead.
Sir, so sorry to disturb you again, but I have two questions, sir. So the first question is that, sir, what's bigger than infinity and beyond? And the second question is that, is omega and LF is bigger than infinity or not? If it is bigger than infinity, so what's the reason behind it?
I'm sorry, you have to speak a little slowly.
Sir, I'm repeating. Sir, the first question is, what's bigger than infinity and beyond? Infinity and beyond. Which one is bigger? And the second question is omega and LF. Sir, are you getting?
Omega, what is omega? Aleph I know.
Hello?
Omega I don't know. Aleph I know.
Sir, LF, yes, sir. Sir, Hebrew alphabet. Sir, it is Hebrew alphabet, sir.
What alphabet? Hebrew alphabet. Yes, Aleph comes from Hebrew alphabet.
Yes.
Omega is from Latin, from Greek.
Sir, is omega and LF
Omega
is
is
bigger?
from Greek.
Yes, sir. It is bigger than infinity or not?
Well, this is again, this is the problem. You have to learn these things properly. This is Cantor did what is called essentially comparing infinities. The attempt at comparing infinities was started by Cantor, the German mathematician. So the infinity, countable infinity, that is what he called, or later on called, Aleph naught. And then the uncountable infinity, Aleph 1, etc. And then there could be even larger infinities. So he introduced the concept of ordinal numbers and comparing them. And that is how these objects were created. Remember, they were created. There is a famous statement due to Kronecker. Have you heard of Kronecker? Kronecker delta you have heard. So Kronecker was a German mathematician, number theorist. He said God gave the natural numbers 1, 2, 3, 4. Rest are all man's creation. So similarly, Aleph naught, Aleph 1, etc. These are all man's creation. To Cantor in particular, comparing various infinities. Now, one of the biggest problems were he could not prove whether there is an infinity between Aleph naught and Aleph 1. Okay. In fact, later on it was proven that this cannot be proven based on the given axioms that one usually assumes.
Yes, sir. Here my question is,
This continuum hypothesis, that is, there is no infinity in between Aleph naught and Aleph 1, that is an assumption. This neither can be proven nor can be disproved. You can learn about it. There are many popular books written on it. You can read a little bit on it, but it is a part of what is called mathematical logic, and it is a different kind of area of subject where you argue and decide in favor or against these things. Whether the axiom system is consistent with having these infinities or one bigger than the other, in what sense, these are all parts of mathematical logic where you study the completeness of the axiom system. There are many dichotomies and undecidable propositions in the foundations of mathematics. So one should not say mathematics is a completely finished subject in that sense. If you go to the very foundations of mathematics, there are issues which are not completely decided or probably not decidable. But then I am not an expert on those, so I will not say anything more.
I think there are so many questions we had answered, and participants are. It's okay.
So,
With this questions, let us thank Professor Sinha, sir. So, sir, I think there is no questions other than this is the last question, I think, and the infinity is depth, and I do not
Yes,
see any question.
I think let this be the last question because I have to go get some lunch, otherwise they will close. Okay, so let this be the last question.
Yeah, this is the last question, and no more questions. So let us thank our speaker, Professor Sinha, sir, and we are late in the beginning, and we are very sorry for that. We are sorry to, I will say to sorry to each and every participant, and especially to Professor Sinha, sir, as we are not because we have should have, being a mathematician, we should have the habit to be punctual. So we did not, we did late. For that we are sorry. And with this, I would like to thank all and all.
Mr. Suman Kumar, I would like to interject that
Yes,
the
sir.
habit of being on time
Yes, sir.
is not just a mathematician's responsibility. It should be everyone's responsibility.
Yes, yes, sir.
Everyone.
Yes, sir. This is right, sir.
Okay,
Yes, sir.
thank you. Thank you.
Thank you so much to each and everyone.
Okay, thank you all. Bye.
Yes. So now we request the participants to continue for the next lecture. Professor Dhankar sir is coming online, and we shall start. We shall be continue there. Yes, sir. It's too late, sir, and just now it is finished, sir. Sir, now connect, sir. We are online, sir. Yes, sir. Yes. It's. Oh. Yes, sir.
No problem.